Hi, my name is Isabella Torres, and today I'm going to be talking about a technique to use known intents and possible faults to project trajectories in swarms and then use that for better cooperative localization and collision avoidance. So this is a part of a joint project with NASA JPL. Specifically, they have the Cadre mission, or Cooperative Autonomous Distributed Robotics Explorers. And this mission is going to launch to the moon in 2024 with the goal of performing autonomous collaborative exploration. So being able to safely explore as much area as possible is incredibly important for the success of this mission. Now, these rovers require a lot of collaborative navigation in two different senses. First, these rovers need to do a lot of collision avoidance in order to get around the obstacles that they discover, as well as avoid collisions with each other. Second, the system requires cooperative localization. The rovers currently do not reach the high localization accuracy requirements from NASA in order to have good science data. And so in order to get around this, they use UWB ranging sensors in order to get relative positioning between the rovers. Now, these ranging sensors give better information when you are in certain geometries in the swarm. For example, the geometry on the left here, you're going to have not as much information coming from that because the rovers are all in the line versus the geometry on the right. So in order to maximize this, you can imagine a path planning algorithm where the rovers are actively cooperating in order to improve their localization as a whole. Now, both of these things are hindered by the fact that it is possible that communication will drop as the rovers are completing their mission. We know that you might start off having communications and then lose that in the middle of moving towards the goal. Now, there are multiple different causes to this. There could be electromagnetic interference, obstacle occlusions, or power loss or some other agent fault. And the problem is you don't know which one of these is the case. And so you can't assume that there was an agent fault. The agent could be still moving. You can't assume that it was an obstacle occlusion because the agent could be dead. So the question is, what do you do when you don't know what has happened? Worse, you can consider that since these rovers are exploring their environment, if they discover obstacles on the path to their goal while they aren't communicating, that could alter their trajectory such that the trajectories interfere with one another, causing a collision. So the question is, how can collision avoidance and cooperative localization remain robust under communication loss? So we have a few different prior works that are relevant to this research. First, we're going to look at reachability-based trajectory design, or RTD. The idea here is you're doing reachability analysis on the rovers. You're finding the set of states that is possible for them to reach. Then you can consider, as we're doing path planning for the top rover, we'll consider what is the reachable set of states for the bottom rover, and it acts sort of like a dynamic obstacle. So that set of states it can reach creates this unsafe set of states that both agents could reach, but where a collision could occur. Then there's also the safe set, which is the set of states that the first rover can reach, and it would be fine if it navigated there because it would not be at a potential of colliding with the other rover. Now, this in theory should guarantee no collisions, but the problem is that, for example, the goal might be inside the unsafe set, in which case you never collide, but you also never complete your mission. There also is no mean prediction of where that other rover could be. It could be anywhere within the unsafe set, and reachability-based trajectory design doesn't really prescribe where it might be. You can consider another case where the agent is inside the unsafe set, and reachability-based trajectory design doesn't really prescribe how to move out of that unsafe set in the way that reduces the probability of collision now that collision is absolutely possible. There's no way to 100% avoid it. Another area of research we looked at was intent prediction. This has mainly been done in self-driving cars, where you can consider a case where a car is at coming to an intersection on a road, and you know it can go straight, left, or right. And the autonomous car wants to predict where that car might go so that it can avoid a collision with it. Now, a lot of this research treats those different directions as modes in the potential trajectories that the car could take. The problem with applying this to lunar exploration is that you don't have a clear, distinct set of three modes. The rovers could drive anywhere. It's a much less defined environment, especially because it is actively being explored as the mission is carried out. This also neglects the known goal. We know, because the agents used to be in communication, we know where that agent is trying to head. And so we should be using that information in order to narrow down what trajectories it might take. We also look at fault-based trajectory planning as an area of research, and we weren't able to find much prior work on this. One of the prior works we found was specifically for single agents and planning a trajectory in response to their own faults. For example, a broken wheel, how does it change how a trajectory plans? That doesn't apply as well to this multi-agent system we're considering. We also found a lot of cases with UAVs, where if an agent is lost in a swarm, the swarm might reform formation in order to work without the UAV and accomplish goals without that lost UAV. There's a couple problems with this. One, when you're on the moon, your agent that has died is still there on the moon with you. If with the UAV, a dead UAV will drop out of the swarm, out of the sky completely, and it's no longer in the sphere of where they're operating. That agent, lunar robot that has died, is still on the moon with the rest of the rovers, and it is now an obstacle for them. And so it can't just be ignored. It also might still be moving because we don't know for certain that a fault has occurred. And so we have to be able to address both of these issues. So, with the previous three approaches, clearly each lacks an ability to appropriately address the problem at hand. And so in this work, we will be combining all three. Our contributions are expanding upon RTD, intent prediction, and fault-based planning in order to enable navigation strategies through the unsafe set of states, enable tuning risk sensitivity to achieve desired performance, as well as create a probability distribution describing the likelihood of the rover being in different states in order to enable use for cooperative localization. So for the rest of this presentation, I will start by giving a little bit more background on reachability analysis. I'll then go into the approach and the various different aspects within that, and then talk about the experimental validation. Now, reachability analysis can be done with zonotopes, which are set-like objects constructed from a center point and a set of generators. Essentially, anything within that set is considered a place where the rover could be. Now, a sequence of zonotopes can be used to represent the set of states the agent can possibly reach, or the forward reachable set, or FRS. Each zonotope within that FRS represents a different time step. So the first square could be time 0, and then you have time 1, time 2. The amount of states that the rover could reach grows because it could be traveling for a longer period of time. In order to calculate the forward reachable set, we consider the planning reachable set and the error reachable set. The planning reachable set is a set of states an agent could reach given different control inputs, for if it goes straight, left, or right, how fast it's going, for example. The error reachable set is a set of states an agent could reach given various sources of uncertainty. For example, if you know in the beginning that you have a certain localization error, you can incorporate that into the reachable set of states. Now, because of some of the math behind zonotopes, there's this thing called the Minkowski sum. So you can directly add the planning reachable set and the error reachable set in order to get the forward reachable set. Now, that was all previous work with RTD. In this work, we're also going to be incorporating probabilistic zonotopes, which are set-like objects, again, which also have a center point and a set of generators, but now they also have a covariance matrix. And so that describes a Gaussian distribution outside of this uncertain mean that's represented with a normal zonotope. And it becomes more of a probability distribution. It is a slightly more complicated set of objects. Now, the key characteristics, you have the same set operations as normal zonotopes. You have the uncertain ability to represent an uncertain mean that you have with normal zonotopes. And you can also have a probability distribution derived from the Gaussian distribution. Okay, so that's it for background. Getting into the approach. We have the intent-based and false-based aspects of the approach that I'll go over. Then I'll get into how we combine those in order to make it usable for path planning. So starting off with intent-based. With intent-based trajectory prediction, we know the goal state in the agent's last published local plan. This will be what, before communication was lost, the agent communicated to the other agent what it was planning on doing, what its planned trajectory was. And so we still have that stored in our memory. Now, the first step is to generate probabilistic zonotopes along each point of the local plan. And this will describe the uncertainty in whether the agent will replan and take a slightly different route from the local plan. Then, as the local plan may not reach all the way to the end goal, we generate a straight line from the end of the local plan to the goal and generate probabilistic zonotopes along that as well. So some important parts about this, the covariance matrices, those are determined through tuning and calibrations through a lot of simulations. And they represent uncertainty in what trajectory exactly will be taken. And they increase with distance from both the last known position and the goal state, because those are the two fixed points we know that the rover is trying to get to. And so those points are the most certain, and the points in the middle are much less certain. The path it takes to get there is less certain. Next, I'll get into fault-based prediction, which follows somewhat of a similar approach. We now know the probability of a fault and the resulting trajectory. We will mainly focus on the case of just a dead agent. And so the trajectory is just not moving. Again, we generate probabilistic zonotopes in this case at its last known location. We then store this forward reachable set alongside the intent-based forward reachable set. And now we have two different representations of where the rover could be based on whether we're considering the known intent or whether we're considering possible faults. And so now we have to combine these two, and we do that via time-varying weighting. So we know that communication loss could be caused by this fault, this power loss, or it could be caused by EMI or occlusions. But as the length of time without communications increases, the likelihood that the cause is power loss increases, because it's much less likely that you had sequential EMI for this long duration of time. So the zonotopes generated for intent and fault-based trajectories are weighted differently over time as it becomes less likely that the rover is still moving. You can see an example of this where the point around the origin, the fault-based FRS is increasing in probability with time, and then you have this intent-based FRS, and over time it is relative to this other FRS not as large. Now, that is great, but we also need to be able to incorporate it into some path planners. And so in this work, we're considering a path planner that just takes in normal polygon obstacles and plans around them. And so in order to be able to feed these probabilistic distributions into that path planner, we're going to have to bound the probabilistic zonotopes. So for collision avoidance, we can convert these probabilistic zonotopes back to regular zonotopes and then treat them as obstacles. The new zonotopes bound the unsafe set in a way that is much less conservative than what RTD did. So the zonotope generators will also depend on what the risk tolerance is selected. You will end up with a much larger zonotope if you're doing, say, 90% bounding versus 50% bounding. And this 90 versus 50% is based off of the cumulative distributive function for the Gaussian distribution related to that zonotope. Now, getting into some experimental validation, we implemented all the previous things I talked about on turtlebots that were simulated in Gazebo. We assumed that there was constant communication loss, as is the case that we were most concerned about. We randomized the starting and goal positions. So you can see on the right an example simulation where you have a starting position and a goal position for Turtlebot 1 and a starting position and a goal position for Turtlebot 2. We also have 3 random obstacles, and then we occasionally simulate faults as well. Now, we ran many different simulations. We're going to focus on just this example simulation in order to talk about how this algorithm worked. So this also shows what it looks like for us when the simulations are being run. The obstacles that are generated are like virtual obstacles that are being fed into the robots. They're not visible, but you can see the rovers moving towards their goal positions. So we'll start off talking about the control cases. First, with no collision avoidance, you can see the rovers just go directly to their goal. This blue line here, right here, this is the local path plan that was last received before communication loss occurred. And then this is connecting the end of the local plan to the goal, as was discussed earlier. Now, they don't collide because they weren't on a collision course. They just ignore each other and make it to their goal. With prior work with RTD and just normal zonotopes, you can see that we generate a zonotope starting at the beginning, and it really rapidly grows in all directions from the start. Now, this is somewhat unrealistic and over-conservative because we know the goal is over here. It's highly unlikely that that rover will try to drive straight up the screen because that just wouldn't be getting it towards its goal position. And so this work was trying to make this somewhat more realistic to what the rover is actually going to do, rather than bounding every state it could possibly reach, regardless of its goal. So now we look at the same graph, but with our different bounding approaches. We look at first 10% bounding, and so the square that stays centered on the original starting point, that's the fault-based FRS. You have this zonotope that's moving with the agent. That is the intent-based FRS. And then you also see the third square that's in the beginning, and that's just sort of looking forward into the FRS and keeping in mind the future potential state of the rover for the purposes of collision avoidance. And so you can see that this is much smaller than what was on the previous screen, and it actually follows the trajectory. It's not predicting that the agent's going to move up here. For 50% bounding, now you can see that the FRS is growing much larger. And so this is covering a much larger portion of the screen, but it's still following the trajectory we actually expect. And for 90% bounding, it is covering a even much larger portion of the screen, but it's still following that trajectory. So what you might want to consider in tuning is that when you get up to 90% bounding, clearly the approach is less useful than with 10%, but you might have a risk tolerance that suggests 10% just isn't sufficient bounding. As on another side note, talking about the behavior of the turtlebot up here, the one that is reacting to these obstacles. In the 50% bounding case, it starts out here, it's outside the zonotope, but it gets sort of caught. It wants to go around the bottom of this obstacle, but it can't because it sees this expanding obstacle. And when it hesitates, it gets overtaken by the zonotope. Now, the path planner that we selected, when the rover is inside an obstacle, it is fed, it acts as if the obstacle isn't there at all. And so what we see is it hesitates until it's inside the obstacle and then it ignores it, which is a particular behavior of the path planner. We could imagine trying to change how this operates, but this just informs us that if the zonotope grows too fast, then it is no longer useful for path planning. And of course, that happens very quickly with 90% bounding because the zonotopes are so large. Really, the most desired behavior is most similar to the 10% case, but again, that depends on your risk tolerance. Now, for next steps, all the turtlebots that we saw in simulation are also real turtlebots that exist at the flight room at Stanford. And so we want to actually implement these algorithms on the real turtlebots in order to get some hardware validation going. So, in conclusion, the proposed approach improves upon RTD in order to avoid collision in the unsafe set of states. It also reduces conservatism as your risk tolerance allows, and it enables active cooperative localization even with large amounts of communication loss by providing an expected state. I would love to extend thanks to JPL for providing support and funding for this work, especially to Dr. Jean-Pierre Delacroix and Dr. Federico Rossi from JPL, who have been a huge help in this project and who have given us a lot of great advice and comments. So thank you for listening, and I hope you read the paper.